Let's continue with activity 11 and do part D, coming up with a predictive model for the customer lifetime value problem. So with the predictive model, it is pretty much just a hack job. As long as it's making predictions on new data pretty well, then we're happy with it. We don't necessarily care about the coefficients, what variables are in it, which ones aren't, what the form of the model looks like, etc. So what we need to do is basically fit a ton of different models and see how well they each predict on new data. So in order to do that, we need to split the data set that we have into two parts. The training set, where we build a bunch of models and kind of pick which one we want to use, and then a holdout sample where we finally assess, how well that model generalizes to new data, because we won't let the model see the data in the holdout sample until the very, very end. So what we do is we first decide how we are going to make that split into training and holdout. So it's always a good idea to set the random number seed before doing this so that you can reproduce your results at a later time. Otherwise, when you randomly split the data set into training and holdout, you're going to get a different split every time, and you can potentially get different results with that procedure, because a different split might give you a potentially different inferred predictive model here. All right, so we're going to set the seed to be 320, and then we're going to run the command train.rows left arrow sample boop 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 here. So what does this do? Well, what it's doing is the first argument of sample is saying what numbers you're going to pick from. So in this case, 1 colon n row value is just going to be the integers 1, 2, 3, 4, 5, 6, etc., all the way up to the number of rows of our value data frame. So it's basically going to pick row numbers at random from our value data frame. And the second argument tells us how many numbers that we want. So in this case, I'm going to take a sample of row numbers that's equal to 60% of the total number of rows in the value data frame. So in other words, I'm going to be putting 60% of the data into the training set and the remaining 40% into the holdout sample. So I'll run my train rows. And then what I do is I split up my original data. So values my name of the original data frame, and I just want to put in certain rows into the training set. So the way that I do that is to put square brackets after the name of my data frame and put a comma in between those square brackets. Now, whatever comes before that comma is referring to the row numbers that I'm going to be extracting. And in this case, train.rows provides me with the list of rows that were randomly selected to fill in that training set. So train rows, comma, and then usually I leave the space after the comma blank because I want to be using all columns in my original data. But in this case, we want to exclude that first column because that first column corresponded to customer ID, which doesn't contain any information about their value. So we'll run this, which will define a new data frame, train. Notice it has 300 observations. And the holdout sample, I basically want to put all the rows that didn't go into train into holdout. So I can do that pretty easily by typing out the name of my data frame, value, and then in square brackets, before the comma, I'm going to put the row numbers that I want to be putting into the holdout sample. And in this case, I want basically everything but the row numbers that were put into the training. So if I do minus train rows, that'll do every number that wasn't in the vector train rows and put that into holdout. That'll accomplish exactly what I want. Minus 1 after the comma because I don't want to include that first column as a predictor. So I'll run holdout. And so we see we have 200 observations in the holdout sample, and we had 300 observations in the training set. All right, so with the training set, what we're going to do is fit a ton of different models and then estimate the generalization errors of each of them. We want to estimate how well we think they might be able to predict on new data. So the way we do that is with repeated k-fold cross-validation, and you can read about how that works in the notes. But basically, in the training set, we siphon off a little bit of it to serve as a validation set, estimate coefficients with the remaining training data, and make predictions on that validation set, which the model wasn't using when estimating the coefficients. And that gives us a good estimate of the prediction error. And we repeat that a whole bunch of different times to get an overall idea for how well we think the models might generalize. All right, so how we actually implement this in R is to use the command build model, and that'll go through and try out a whole bunch of models for us. So when we use the command build model, typically what we do is we say, all right, well, what's the formula of the most complex model I want to consider? And in this case, I want to be predicting customer lifetime value. And I might want to consider all predictors and all in two-way interactions, in which case I would do customer twiddle.squared. But when I do this, it's going to give me a little warning that says, hey, you're about to try to fit basically 3 times 10 to the 20 different models. So are you sure you really want to do this? And no, I don't want to do that because that's going to be too many models. It's going to take way too much time. And if I commit to saying yes, then R is going to do it until the command is completed. There's no way to stop it. You'd actually have to force quit RStudio and just restart it if you didn't want to spend all that time. So in this case, what we're going to do is we're just going to consider the predictors found in the model found with the search for our descriptive model here. So I could go back to the output of the regression model and basically just get in these predictors here, but that would be kind of tedious. So there's a shortcut actually. There's a command called formula that will extract the formula used to build any particular model. So I named that descriptive model S, doing formula S. Notice that, bam, there it is. There's the formula. So in effect, what I want to do is I just want to consider the most complex model to be this one found here, along with maybe additional two-way interactions if they're necessary. So what I'm going to do is, for right now, do prompt equals true so that I am warned if it's going to take a long time. And I'll run the build model command, saving the results to BM. So this says, hey, there's about 1 million models you're about to consider. Are you sure? Yeah, actually 1 million models isn't all that bad, so it'll complete fairly quickly. And the key thing is that when you do build that model, remember to do data equals to train. You don't want to use your entirety of the data set. You're just looking and considering models that can be built on the training data. All right, so it looks like my plot got messed up, so I'm going to fix that by doing par mfrow equals C11. Right now it's still in the mode where it's trying to make more than one plot on the panel here. And so I'm actually going to run this again. So making sure data equals to train when you do build models is a key thing. And also making sure that the seed is set is a key thing so that you can reproduce the results. So the estimated generalization error of each of the models under consideration is found with k-fold cross-validation, which is a random procedure because it's splitting up the training set into a validation sample as well randomly, and it does that a whole bunch of times. So if you don't set the random number seed and you run this command more than once, you're very likely to get different estimates of the generalization errors, and therefore you might actually choose different models. Nothing wrong with that, but if you do want to reproduce the results, or if I want to grade these, then I need to make sure that the seed has been set so I kind of can anticipate the answer here. So, all right, I was waiting, but I forgot to say yes. So it's continuing, and it'll have this done shortly. All right, so I'm going to change this back to prompt equals false so that when I compile it, I don't have that prompt kind of messing up everything. So I'm going to remove that, remove eval equals false here. And then what we're going to do is we're going to look at the CV table of our results. So BM, the name of build model, is a $CV table is going to give a list of models that it's plotting over here. Basically the number of predictors in that model and that model's estimated generalization error along with the standard deviation of those estimates. So repeated k-fold cross-validation happens 10 times. We get 10 different estimates of the generalization error. The standard deviation of those provides a rough measure of how much we've nailed down the generalization error of the model. The standard deviation gives us a little idea of that uncertainty here. So overall what we see is that, sure, adding in more and more predictors makes the estimated generalization error of the model improve. Up to a point, it looks like the model with the lowest estimated generalization error has 14 predictors, with a star over here, and the value of the estimated generalization error is just a smidge over 40,000. And we see signs of overfitting as we put more variables in because that estimated generalization error is actually increasing by a little bit. All right, so how many predictors are in the model with the lowest estimated generalization error? Well, we see 14 different predictors. How many are chosen with the one standard deviation rule? So if the one standard deviation rule says that, all right, there's a little bit of uncertainty regarding the estimated generalization errors, so don't necessarily go for the one with the overall lowest value. You can get away by choosing a simpler model as long as its estimated generalization error isn't too much worse. So how much worse can it be? Well, we look at the standard deviation of the estimates with the model with the lowest error here, and we basically add these two numbers together. We're going to choose the simplest model with an estimated generalization error that has an error at no more than one standard deviation above the lowest value here. And so that's what this plus represents. It is the simplest model whose error isn't too much larger, at most 7,600 above the error of the overall lowest. So in this case, we see that there's 4 predictors in the model chosen with the 1 standard deviation rule. All right, do we see signs of the model becoming overfit? Yes, we do. So after, any additional variables added to the model after the 14th, what we saw is increasing the estimated generalization error. All right, so we do see signs of overfitting. All right, so what we would do is basically make our decision at this point. We can go with the model selected by the 1 standard deviation rule, which is typically what we end up doing, or we can just choose the model that had the overall lowest estimated generalization error. There's a huge difference in the number of predictors, and when making a predictive model, actually simpler is very often better. Models very often get overfit, basically have too many predictors and memorize quirks on the training data, leaving them not able to generalize as well to data at large. So we would make a choice and probably choose the model with 4 predictors in it. So I could actually do $BM$ and then predictors, and I could do double square brackets in this case. I won't explain why, but we need double square brackets in this case 4, and this tells us what 4 variables we would need to include here. All right, so we've chosen our final model, and I'm going to say this is our final model here. And it's always interesting to see how well we end up actually doing on genuinely new data. So we've had this holdout sample all along. We've set it aside. We haven't looked at it yet. Let's use our final model to make predictions there, just to make sure that the estimated generalization error seems to be pretty reasonable, that we actually end up making errors on genuinely new data about as large as what we anticipated. All right, so I'm actually going to go down here and run these commands first. What we're going to do is we're going to modify our training set and holdout sample to reflect just the predictors that are in this model, basically just the indicator variable representing if you're high income or not. So I'm just going to run these commands verbatim. And so what I'm doing here is I'm adding in a new variable called income F90 to infinity that is either a 1 or a 0 depending on if the income level is or is not equal to that level. Because this model just wants that indicator variable, the only way I can make R do that is to manually create that column. So I will do that for the training set and the holdout sample. And now what I'll do is I will fit that model that had the lowest estimated generalization error within 1 standard deviation. So here's the formula, total transactions we see. Total transactions and the interaction between that and wallet share, so separated by a colon, not the multiplication sign because we don't need wallet share by itself. Then the interaction between wallet share and income F90 to infinity, and then the interaction between wallet share and first purchase. So let's fit that on the training set and finish off that line, and then see what that model's generalization error is. So generalization error is the command I'll use. I say what model I'm considering, and then what data values am I making my predictions on, the holdout sample. All right, so what I see is that if I use this model to make predictions on the holdout sample, the typical error is 166. So is this a good value? Am I comfortable with this model? And in this case, I'm actually very comfortable with this model. Something very surprising happened. On the training data, this model actually makes an error of 206. So the error made on the data that it was using to estimate the coefficients is actually larger than the error on genuinely new data. And this hardly ever happens because typically, the model is using this data. It's going to fit that data the best that it can. So typically we see the training error be noticeably smaller than the error on the holdout sample. So this is actually a really comforting sign. It looks like this model does generalize very well to new data. In fact, it happened to predict better on new data than the data that was being used to build that model. Kind of an interesting thing here. All right, so how does that compare with the other models we could have chosen? Well, the naive model, if we fit that on the training set and then predict on the holdout sample, we see that using no model at all, the root mean squared error on the holdout sample is 819. So our model is way better than that. What about if we just used all of the predictors to make our model here? So fit the model with like twiddle dots, all the predictors with no interactions, fit that on the training set, predict on the holdout sample. All right, well, our error would be 169. So we do a little bit better with our selected model. That's kind of nice. What about all two-way interactions as well? Well, fit that on the training set and see how well that predicted on the holdout sample. That error would be 174, even a little bit worse here. That model's probably overfit too many variables. It memorized what was on the training set, and it's not able to predict on the holdout sample all that well. What about the model that we fit during the search for a good descriptive model? So instead of typing that formula out, I'll just do formula S since that's the name of the model. Name that model search and then look to see how well that does. And interesting. So I see that its generalization error is 147, which is, quite noticeably better than the model that I selected using my build model command. So, in fact, it looks like that the model that ends up performing the best on that holdout sample is the model found with the search. Do I change models at this point? No, absolutely not, because I don't use any information on the holdout sample to guide myself in model selection. I do all my model selection just based on the training results. And so in this case, I'm not going to change models. I'll stick with my guns here. If I had a different holdout sample, it could be very well the case that my selected model did perform better. So, all right, so my final model, this is the overall error. I'm happy with that. It's actually lower than what's on the training set, a very unusual thing. But like with most cases, there are other models out there that exist that you couldn't anticipate would have actually performed a little bit better on the holdout sample. So, all right, that's some predictive modeling. We basically do our best, and we kind of cross our fingers and just hope that that's okay. So which model ends up with the best on the holdout sample? The model found with the search during the descriptive modeling task. So our predictive model was not the winner. And really, it rarely is. You're rarely going to choose the best predictive model, the one that ends up happening to predict on new data the best. We basically, to the best of our ability, use the information available to us, pick one that we think is going to do pretty well, and just hope for the best here. All right. So there we go. That's question 1.